All right, guys. So let's review infinite series. Do you remember infinite series or they are forgotten? So let's begin with this problem. Let's see if we remember it. I am a generous person, at least some claim so. Maybe me. So I will like to give you a gift. And in my gift, I will give you $2 to the $7 plus $2 to the $8 plus $2 to the $9 plus $2 to the $10, and you understand the pattern. Please sign up if you would like to receive that gift from me. So how many of you say yes? Ryder says yes. Steven says yes. Albert says yes, please. Good. Cindy, what is 2 to the power of n? Cindy, that's just a letter. So, right, you just this and it just represents for a particular value. All right, so I'm very glad that you trust me so much. So, how much, if you want to get it, how much are you gonna receive? Okay, Barry wants only from, but n Barry n is is just not a number, right? So you don't tell me how much you want. All right, so how much do you get, guys? Well, let's see. You get something. Do you agree? First of all, you either get something or you don't. So let's say you get something. So look at this formula. Something is equal to the summation. I can just put in red parentheses. I can put everything else. I'm trying to make this monster look simpler and more manageable, right? So 2 to the n and onwards looks like s. And to make it look exactly like s, I need to factor 2. Do you agree? So it's 2 to the 7 plus 2 times this expression. Do you understand what we just were able to do? We just have s is equal to 2 to the 7 plus 2 times s. And when I solve it, we see that s is equal to minus 2 to the 7 or minus $128. In other words, that you have now to send me $128. I think if you really need to, I'll install Zelle. Now, as I mentioned, I like to give you some gift, guys. You know what gift means in German? That's one vocabulary word that you should remember. Das Gift is poison. Now, what has happened here is again, guys, you can still argue with this calculation. It is in terms of calculus. I mean, you are trained to look at it as a calculus student, and that means that you understand that the sum is 2 to the 7 plus 2 to the 7 plus 2 to the 8 plus, you kind of expand your horizon like this, right? So it's clear that as you do that, the amount of money you receive is increasing. But the idea, again, not very well defined in how I just calculated it. The idea is I throw this money in one batch at you. And if I just kind of take it and throw one batch at you, if that makes sense, and then what you get is minus $128. Some student mentioned it's like an inflation, I suppose. That's how they made sense of it, right? When you can give so infinite money, that means the inflation is so bad that you get minus $128 in this case. But yeah. We would like to understand how sequences work first. So a sequence, strictly speaking, is a function from the integers to whatever you want to order in a sequence. and this is just, this function is just telling you what's the output. So for example, f of n equal to 1 over 2 to the n plus 1 means that this is telling you how the integer was processed to make the term in the sequence, right? So that represents the sequence 1/3, 1/5, 1/7, and so on, right? The sequence 1, 2, 6, 24, and onwards, this looks like the sequence a sub n equal to n factorial. That's usually how you write it. You write it as n sub n instead of this f of n, but it's not going to be terribly important for our course, so I'm skipping over it, but you should know that a sequence is a function. Good? It's a function from, it's basically a function from the integers, from the positive integers. And we might have a n equal to 10 to the minus n, and we can try to understand what's delta epsilon supposed to do. That's a bit important, right, for our understanding of what probability is later on. So delta epsilon, guys, do you know the arguments? Do you understand how they work? Or the, you know, the epsilon arguments? Yeah, well, I mean, proof of limits, yes, right? So for instance, if you look at a sub n, I just gave you a very simple sequence, right? Let's try to understand it intuitively. This sequence appears to converge to 0, correct? As n goes to infinity, the sequence converges to 0. What do we mean that the sequence converges to 0? Well, what I think it means is, look at it, guys. If you list the sequence, here is the sequence in a row. Basically, here is the input, and here is the sequence in one row. Sorry, one column. So here is what happens. As you look down the sequence, you stop telling the difference between the sequence and 0, right? Eventually, you look down, it looks to you like 0 written is in one row and 0 is written in the next row and onwards, right? So notice that, for instance, if I have epsilon, that's my resolution, 10 to the minus 6, that resolution means that I am able to distinguish 0 up to 6 decimal places. You understand? That means that starting from the 7th decimal place, if all the decimal places are 0, starting from the 7th, I think it's 0, even if it's not. Good. So you can see that here in the blue, I can tell that this is not 0. But starting from 6 and onwards, I cannot tell anymore that this is 0. That's what epsilon, for that epsilon, for that resolution, starting from capital N, starting from the 6th row and onwards, everything looks to me like 0. You understand? If I select a smaller epsilon, it would start happening slower, but there would be a row, capital N, from which, for that very epsilon, I cannot tell the difference between the input and the convergent value. You understand? Here is the definition, guys. A sequence an converges to the value L if for a given epsilon bigger than 0, there will exist an initial starting integer, and basically starting from some row, such that for all rows beyond that integer, I will not be able to tell the difference between this value and L, right? Like in this row. So for example, if I selected a specifically easy sequence, so if it's 10 to the minus, if it's 10 to the minus 6 that I use, then starting from the, let's say, 7th row, I am sure I will not be able to tell whether it's 10 to the minus 6, minus 7, minus 8, if those things are different from 0. Yes? You understand, guys, the idea of this definition? It's the idea of this. This is the way you conclude with limits, right? It just, if anyone looking at the sequence eventually starts thinking that it's the convergent value, then that's how you know the sequence converges to that value. And you have to be precise what you mean by anyone. So take any detector that has a particular ability, particular expertise at telling something apart from something else, right? So in this case, it tells numbers apart from L. And if the expertise is of value epsilon, there is going to be a point where where there's going to be a row. Starting from that row onwards, this machine, this detector cannot tell the difference between input and the value L. Yes. So far clear, guys? Now, important limits. Yes, but what I mean is we don't have to necessarily prove all the time, but we would like to know how to do that using delta epsilon, what it means exactly for convergence to be. So 1 + 1 over n converges to 0 as n goes to infinity, and we know that because one way to verify that rigorously is to use this delta epsilon criteria, right? Or in this case, capital N epsilon. It means that this number 1 + 1 over n -1 will eventually be too small for a resolution epsilon to detect it. For a detector, so whatever. So here is an important limit, guys. Again, look at this row afterwards. When we will try to explain a very, very difficult idea, guys. What is probability? Right? We will use this sequential approach. So I hope that you would understand what is it that you are looking for. Right? So convergence means that starting from some row onwards, it looks to you like the rows are filled with the same value. So here is an important limit, guys. What is this limit? 1 + h to the 1 over h as h goes to 0. Do you recall this limit? Write in the comments. What is the value? Right, Gustavo? 1. Somebody says something else. 2 people say something else. Okay. So I do see that some people remember it. So let's try to understand, guys, why the answer is E. It is true. The answer is E. So I don't take any, well, I'll show you how I get to it. It's not a simple limit. It's not easy to figure out what happens with it. So some people are tempted, definitely when they begin taking calculus, they think, oh, it's 1 plus a small number to the power of essentially infinity. So 1 to the power of infinity, they think is equal to 1. Or, there are other errors, but what's happening is much more complicated. So then we go back to derivatives. I hope you remember derivatives, guys. And there is this differential equation, derivative of f equal to f. And recall that if I try a solution of the form a to the power of x, then the derivative will go like this by definition. Yes? By definition, it's a to the x plus h minus a to the x divided by h. Here, I can factor out a to the x. Look at it, guys. I factor out a to the x, I move it across, and I see that it's a to the x times this limit. And this limit looks like the derivative of this limit here, looks like the derivative of the function at 0. So a to the x, you can calculate its derivative as long as you can calculate it at 0. You see what this is telling us? In other words, the derivative of this function is the function multiplied by 0, or some scalar multiple times the function. And we would like to adjust this constant a for the scalar to be equal to 1. That's the simplest possible situation. So limit as h goes to 0 of e to the h minus 1 over h is equal to 1 by the there supposedly exists a number e that satisfies this relationship. Are you with me so far, guys? Wonderful. So we have this idea that derivative of e to the x is e to the x. You see, guys, we are working like this. There is this joke that's rather interesting. A mathematician and engineer are on an island. And they are starving, and then they see a can of soup float their way. So the engineer is busy trying to figure out how to eat. And then he looks at the mathematician and he already is done eating. He asks him, how did you do that? And the mathematician replies, I had a brilliant idea. I assume I had a can opener and I work from there. Yes. So what is the can opener in here? You see, guys, so you play around, right? Look at it. You begin with exponential functions. You know rather little about them, but the fact that you have this exponential rule, let's say, you factor it out and you see that you don't calculate the derivative. You don't know how to solve it. You don't know how to solve this limit. But by going through this procedure, you can just nominally see that if the derivative exists, it's a scalar multiple of this function. Yes, scalar multiple of this function, and you hope for what's scalar. You hope that the scalar is equal to 1. That's the easiest solution. Yes, and then you say, well, let's suppose we actually find a number e for which the scalar is equal to 1. Yes. For which this limit is equal to 1, and then I will try to figure out what this number must be later. But right now, I imagine it exists without any good reason that it does. Here it is, yes, without terribly good reason that it does. I just assume it exists, and then I think, okay, derivative of e to the x is e to the x. So then we have, and this now is a bit difficult, guys. Now we have this limit. As h goes to 0, f of x plus h minus f of x divided by h equal to f of x. Yes, now if I drop the limit as h goes to 0, it's the same. This limit function, this fraction is very similar to f of x, right? The limit just telling me that h has to be smaller and smaller and smaller for this to be a true equality. But if I remove it, then I have kind of equality if it's very, very small. Yes, so then I solve algebraically this approximation, and I see that f of x plus h is approximately equal to 1 plus h times f of x. And I realize I can relabel it. Look at it. This is f of a number is approximately equal to 1 plus a small step back, f of the number prior. So here is what happens here. Essentially, look at it. F of a number is essentially 1 plus a step, the number minus the step. So I create a recursive algorithm. You understand? So it's a recursion. Just like we solved today a problem with recursion, that's a recursive algorithm. That's 1 plus a small step. Okay. So then I'm going to figure out what's going to be the value of f of x in general. What's f of x in general? Well, f of x in general, I'm going to walk all the way down until I get to 0. You agree? Because e to the 0 is where I know the answer is 1. So then what do? I will take the interval from 0 to x, and I will divide it into n steps, where n is a huge number, billions, trillions. The more, the better, because the bigger the n, then the smaller is x over n, and then the smaller is the step, and then it's more like the derivative formula. Do you understand, guys? You see, it's just this. You should understand why I can drop the limit and under what assumption I can drop the limit. And then I have a recursive formula, and then I interpret this recursive formula. It tells me the function at a number is 1 plus a step, the function at the number minus the step. That's what this means, really. Yes. So then I want to walk all the way to 0 to figure out what's the value at x. So I divide this interval and I begin walking. Yes, I walk. There is one step. Then to evaluate this value, this function at x minus x over n, I walk an extra step. So then I factor out 1 plus x again, and I have now 1 plus x over n squared. Now I walk 2 steps, and I finish walking after n steps. This is what I get. So f of x is 1 plus x over n to the power of n. And then you see this algorithm is going to become more and more precise if n is pushed to infinity, right? Because then the partitions are ever finer. So I see that e to the x is equal to limit as n goes to infinity of 1 plus x over n to the power of n. You see this formula, guys? So if whenever I see this, I right away know what's the value based on this x. I have this limit. I figure out that this limit is always e to the x. So here is a quick comprehension check. So what is this limit? Please write down A, what the limit equals to 1 plus 1 over n to the power of n. That's E, right? That's because x is equal to 1, so it's e to the 1. Now what's B? Can you calculate B, please? E to the minus 5, thank you. Thank you, Chiara, as well. Thank you so much. It's e to the power of minus 5. And look at this one, guys, right? So let's look at C and D, and they're kind of very similar, yes? So let's see C, for instance, right? So notice the pattern. The pattern is 1 plus something small. 1 over something small will be E. You understand? That's what it really means. So there I have, what do I have here? This, by the way, can be established again. Here I make another establishment. I know the derivative of logarithms, and you can read this. I'm going to skip it quick. Yes, you can read this. Let's just reestablish it for any h here by this argument, by taking derivative of logarithm. That's just another argument. You can see what happens then. It's 1 plus a small box, but here we have 1 over h. So what is in this box here is not the same as 5h. So I insert 5 and I multiply by 5. Yes, so now this is e to the power of 5. Do you see how I do it? I just interpret. Or in here, 1 minus 2h to the power of 1 over h. I put a box around minus 2h. And then here I put a box around h, it should be minus 2h. Do you see what I do, guys? I just readjust it so that it confirms to this pattern. So I recognize the E from this pattern where this are the same. And I just modify. I call it wishful thinking. I place something in here and I compensate to make it work. Good. And then here is the general situation. All right, so then we still have to talk about series, and then we will have to estimate e to the x. But I wish I could keep you longer, but I'm not sure if you want to stay longer. And that's why I wish you farewell. We are not going to meet, I bet, on Wednesday. Am I right? Wednesday, there is no class, or am I wrong? I think I'm right.
Yeah, there's no class.
I think it's Yom Kippur.
Yes.
Yes. Yes. And it's my birthday, so it's a terrible day.
Happy
No,
birthday.
Yom Kippur is the day of
Thursday,
atonement.
Professor.
You know what Yom Kippur means, right? It's the day of atonement. It's where you pay for all the wrongs that you have done. And this
It's the sad major Jewish holiday. The Rosh Hashanah is like the happy one, and then right on the heels you get Yom Kippur, the sad one. So
yes, exactly. You know what Yom Kippur means? That means to cover for your sins. So yes, exactly. So guys, I wish you all the best. I hope you have a good starving holiday. It's good for the weight I hear. Take care, unless you want to stay.
Auf Wiedersehen.
Auf Wiedersehen.
Thank you.